In this video, we are going to wrap up our discussion of capacitors by looking at the energy stored in them. This is related to electric potential energy. We have to do a little bit more work to understand exactly how much is stored in a capacitor and kind of summarize what we know about capacitors in circuits. So that's the big idea. We know that capacitors can store energy. The reason we know this is because when you charge up a capacitor, and then you connect it to a light bulb, you can get light and heat out of it. So there must have been some electrical energy there. We call the energy stored in a capacitor UC. Usually, it is a type of electric potential energy, but it gets its own symbol because the way we calculate it is not just 2-point particles, right? There's certainly more than that going on. We know how springs store energy. You apply a force, you stretch the spring, right? The area under the curve is our spring potential energy. Right? We know all about that. The work that you do is equal to the spring potential energy. We have this formula. We can integrate FDX, to get US equals 1/2 kx squared. So that idea, the fact that there is some amount of work required to stretch the spring different distances, is really what we're thinking about. And so we want to use that same idea. We talked about how you have to keep, each time you put more charge on a capacitor, it gets harder and harder to add that charge. And so as that happens, you would need to do more work for each additional charge. And so that's the premise, right? You do basically no work to put the first charge on there because there's nothing there to resist it. And then the next one requires a little bit of work, and then the next one more and more and more, right? And so the amount of energy it takes to put it on that plate ends up being equal to the little bit for a little bit of charge is equal to that Q times the potential, because potential times charge is potential energy, right? And so when the capacitor is uncharged, when there's no Q there, then it's easy. But then if you've got it completely charged, it's impossible. So that's the way we're going to be thinking about this. What we're going to do is we're going to integrate the voltage times dq from 0 to the maximum charge, however much charge there can be on this capacitor. We know that the capacitor's voltage also depends on Q, so that's Q over C. And we can find that the capacitor's total energy stored is equal to 1/2 of Q squared, the total amount of charge that gets on it, divided by its capacitance. And since we know Q equals CV, we can actually rearrange this equation in 3 different ways, or 2 different additional ways, to say that if we know the capacitance and the voltage, we can predict how much energy will be stored by saying 1/2 CV squared. If we happen to know the charge and the voltage, 1/2 QV, and so on. Those last 2 are on your equation sheet. I don't know exactly why they picked those 2 and not all 3, but that's what they did. And so we can double check that this all works out. It's joules regardless of how you start. You need to be a little bit careful. These are not the same thing. The electric potential energy that a particular charge has, because it's placed in a potential field, right? Q times V. That is always true for any point particle placed anywhere with some potential. But UC is the amount of energy it took to charge up, or that could be stored in a capacitor by putting the amount of charge in there to get it to that particular voltage. And so those are 2 things. You just want to be careful, right? Single point charge with a potential energy in a capacitor with a total charge Q and a voltage of delta V. Those are the important things to understand there. That's why we use different symbols, even though they're both technically electric potential energy. UC is the energy stored in a capacitor. UE is the electric energy that a single point charge has. We know that electric potential is a property of a point in space, and so that's always true for any individual particle, right? So we want to be careful about that. We can always use that one for those, but this doesn't give us the charge or the energy stored in the capacitor, and that's a little bit different. I did want to do a little bit of a recap here, just making sure we understand where we're at. We've learned a lot of things about electricity, right? Electricity, and next up is magnetism. That's where this inductor column will get filled out. But capacitors, now we have this whole column that kind of matches with resistors. We've already learned about the basics of capacitors, how to add them in circuits. And in the most recent videos, we've looked at how you get the physical capacitance, right? Kappa, epsilon naught, A over D, where the dielectric that's inside of it, the area of overlapping plates, and the distance between those plates tells you how much capacitance you'll have. And then now we have a way of thinking about energy or power. In circuits, resistive circuits, we talk about the power dissipated by a resistor, and then you would multiply that by how long it's doing it to get energy. In terms of capacitors, we talk about how much energy is stored in the capacitor. We don't really talk about power because they get charged up and then they get discharged. So those are kind of the basics. All right, that's it for Unit 10. Next up, magnetism. Very exciting.